मीटिंग में भी 2 लोग हैं। So good afternoon. So last class we have discussed about normal X-ray diffraction, its principle, data interpretation, and today we will see some other X-ray techniques like single crystal XRD, grazing angle XRD, and synchrotron XRD. In addition with this, we will also discuss that X-ray absorption, spectroscopy, and neutron diffraction. So first coming into single crystal XRD. So the single crystal XRD mainly use that rotating crystal methods. Like that other two methods like Lau and powder diffraction XRD. So in case of single crystal XRD, we use most rotating crystal methods. Here you can see here is a X-ray source here, and then here the crystal is mounted here, the center of the rotating axis, and then there is a cylindrical film where you will see the diffraction pattern. So in a rotating crystal method, a single crystal is mainly mounted with an axis that is normal to the monochromatic light, monochromatic X-ray beams. As crystal rotates, the crystal is keep on rotating inside that X-ray machines. So when crystal rotates, so a set of lattice points that has same, satisfy the Bragg's law that will diffract the X-ray beam and you will get a diffraction pattern. By recording the diffraction pattern by both angle as well as intensity, both are we record here at various crystal orientation, the shape, size of the unit cell as well as atomic arrangement like bond length, bond angles, and site ordering can be measured here. So in single crystal allows absolute structure determination. If any unknown material can identify very easily by using single crystal X-ray. So with specialized chamber, you can also do high pressure or high temperature experiment in single crystal XRD. So if you see a single crystal XRD, that mainly rotating crystal method, you will see the sample is here. You can see the center of this ring, and you have an incident beam here is coming on this direction, and then you have here is the sample is here. The X-ray beam is coming in this side, and then you have a beam stopper here. So that direct beam that will stop by this beam stopper, or the diffracted beam that will be detected by the counter the detectors. So here the single crystal diffractor uses either 3 or 4 cycle goniometer. That each cycle here refers to circle here refers to the angles that there are 4 angles. That's the one is you can see here, one is 2 theta, that is that the incident beam to the detector, that angle 2 theta, and then you have a sample rotation stage, that is phi here, and then you have a stage rotation omega, and then another is the chi Jai, that is another rotation. So here this you can see this whole stage on the goniometer rotation. So there are the mostly 3 to 4 rotation in this case, and that defines the relationship between crystal lattice, incident beam, and detector. Depending upon that detector, incident beam, and crystal lattice, so you will have a defined angle of rotation. So sample is mounted on a thin glass fibers. Mostly here that you have a glass fiber on that glass fiber. So you have on this glass fiber that sample is mounted by using epoxy or some specific cements which are attached to the brass pins mounted on the goniometer head. So you can adjust the XY direction such a way that the relay X-ray beam will be the center of these crystals. So that beam stop that I told, that beam stop is mainly here, that to directly beam stops located directly opposite to the collimator, so that to block the transmitted X-rays. If there is, since the single crystal XRD, those crystal may be sometimes transparent, so your the X-ray beam is transmitted through that crystal, so that will be stopped by the beam stop. So you'll mainly see the diffracted beams, and the other reason to keep that beam strap is to prevent burn up of detectors. So if your detector sometimes comes to this position, it can burn up. So you have to stop that. So this is the main use of that burn stopper. And then in single crystal XRD, Nowadays, in modern singular study, uses CCD. Earlier, films are used, photographic films are, so films are used in X-ray diffraction pattern. But nowadays, charge couple detectors are used to transform X-ray photons into electrical signals that are being sent to a computer or for processing. So if you see here, you have a single crystal here, and then X-ray is falling. Then you have to say diffraction pattern that IK you will get. Then you have to Fourier transform that, to get that phase transform. Fourier transformer you have to do to intensity to phase conversion. Then you will see that the electron density map depending upon the atomic position of each what are the element there. So you will see a pattern on the electron density map, and based from the density map you can use a atomic model to create what type of structure is your material. So diffraction pattern, each angle can be used to produce a 3D electron density map that here you will get in case of single crystal XRD. And the most limitation that single crystal must have a say robust sampling technique, and generally crystal has to be large size like 50 to 250 micron size. Then only it is possible to get a better X-ray diffraction pattern. And its sample has to be optically clear. The sample has to be completely optically transparent. And if you have a twin sample, if there is some defects and all these things, so you can come out with the crystal structure identification by using single crystal X-ray, little difficulty. And data collection generally takes 24 to 72 hours. Like in a powder X-ray diffraction, you can collect your data in a big batch data in a 20 minute or 25 minutes, but in case of single crystal XRD, you have to use 24 to 72 hours to get a better data. And after once you get the data, so then the refinement can be done by using different software like CellX or OLX2. So these are softwares are available. So with that software, you can use that electron density map to the atomic model map to find out what are all bond length and bond angle, everything. So this single crystal XRD was fast. The best example of use of single crystal XRD is the identification of DNA structure. If you see, the DNA was, discovered by Rosalind Franklin, who is a physical chemist, a crystallographer. First crystallized that DNA and then photographed vDNA. But in 1953, Watson Crick used this that photo 51 that photograph that developed here. This one using that single crystal XRD, they identify that this is a DNA structure. So if you see this photo 51, what it happened, you can see there is a X. This is the photo 51 in the X pattern. You can see that here that the line draws pink color. So that is the X pattern. It indicates that it's a helical structure. Then in this fourth quadrant of this, if you see, you can see here there is a diamond ring type shapes. So these diamond rings, diamond shapes indicate that long extended molecular molecules there. The DNA structure is quite long, so you can see that indicates the diamond rings. And then you have a similar spacing. You can see the equidistant spacings are there. So this spacing mainly reveals that there is a repeating structure. The DNA has a lot of sugar and base repeating structures that indicates. Then in that there is a missing here. You can see this and this. There is a missing pattern here, and that missing line, that is must indicate the interference with the second helix. Since in DNA the two helical structure, they're superimpose each other. So because of that superimpose, so this particular one is absent. So that's indicate that it is a DNA structure. Then by information from photo 51 they get this a double helix structure, and then that radius is about 10 angstrom, and distance between the base unit is 3.4, and quaternions is about 34 angstrom. So then they combine this data with the other the information that they have, the DNA made from sugar, phosphate, and 4 nucleotides, that the AC, actinine, say especially guanine and thymine, that AC, GT. So all this rule, and then the ratio of this equal to percentage of A and equal to T and G equal to C. So in the molecular modeling by using, so they established the DNA structure here. You can see that 3-4 unit distance that they got from X-ray, and 34 angstrom that distance between the two quatern, so that they found out using X-ray. So similarly, if unknown material, this is unknown material synthesized in lab, that is C32, H36, Cl2, PT, platinum and tellurium compound, monoclinic compound. So you can create a density pattern by using that atomic sites. By you can know the XYZ coordinate and occupancy from the X-ray data. You can find out the cell angles and as well as cell length. All these things you can find out, and finally you can identify this structure using the available software. So mainly the single crystal X-ray are used for analyzing. If you have a single crystals, you have developed a size of about 52 to 50 micron. In that size, you can able to identify from the electron density pattern its crystal structure, and its 3D modeling you can do, and you can find out the bond angle, bond length, and all other information. So in addition to single crystal is another, powder XRD use mostly powder sample. In single crystal, you are using optically transparent material and is grown in it is mainly single crystals. But if you have thin film, so that is not possible in single crystal as well as in a conventional normal XRD. Normal XRD you can do up to if you have thin film is quite a little bit thick, but it's quite fine like nano layer or something that micron size. It's difficult to see by this normal powder XRD. So for that you have to go for grazing angle XRD that is used for thin film analysis. In grazing, if you see the grazing angle or glancing angle XRD that sometimes it's called. So in grazing angle, the incident angle is fixed. You can see here you have a substrate at the bottom, and on the substrate you have this is the coating thickness. You can see the coating on the coating surface. The X-ray, that is incident angle, you can see it's fixed here. That is theta is less than 5 degrees. So X-ray are focused only on the top structure. If you have you can see the X-ray will be on the top surface. If you go on higher angle, what will happen? The X-ray penetration can to go to the if I go like this, it will go to the substrate. So if the angle is very low, your X-ray will be on the the thin coating only. It will not go to the substrate. So here that the incident angle is first of all focused is very low, so that you can see only the topmost surface. Then grazing angle XRD can be performed in many analyses like normal powder diffraction. That things can be possible in this also, and it can get a depth profiling that is not possible in case of conventional XRD or powder XRD, that by collecting successive diffraction pattern in each layer. So if a layer structure that can be possible, you can get information about orientation of thin film with respect to the substrates, lattice mismatch between film and substrates, how the lattice variation between the thin film as well as your coordinator substrates, as well as if you have a structure or epitaxial growth, those things you can see. And if you have a strain, how the strain built up in the thin film, and that strain is affecting shifting of your peak at a lower angle or higher angle, those information you can get. And in grazing angle incident X-ray, you can also in incidence X-ray, you can see the reflectivity measurement can be possible, can be determined to identify the thickness, roughness, and density of the film. That you can also do. Then this technique doesn't require crystalline film. Like with amorphous film, you can able to see if you have a pattern. So you don't use no need of a crystalline film. Here, increasing pathway through the sample, like the main objective is to in the sample, here is the thin coating, in that you are increasing the path length of the X-ray just by fixing the lower angle. So if you see an example here, you can see the omega that here it is fixed. Fixed at grazing angle here, and you can see the 2 theta can be varied, and you can see all the different of the coating that structures you can able to see. So here that this is a main problem is a weak signal from the alternative. Very thin film, you will get a weak signal. Signal is very weak. If you have that can be solved by grazing angle geometry. And if you have overlapping of peak, that can be this stress strain measurement is possible. Even phase identification can be done even if by using this by depth profiling and structure information that you can also get. So you can see here this bottom picture that the all grains are in this direction aligned in the straight line here. And then you can see here if you have a normal here, that particular plane here, which one is this with diffraction pattern, that the Braggs law satisfied with that particular plane, you are getting these peaks. In here you can see that if you change the depth, like this slightly tilting the the sample position or something, or if you this normal diffraction that pattern you can see by this is you can able to see the another plane, this one that the other plane is in slightly oriented in different direction, that you can get an additional peak. Similarly, by changing that normal to the diffracting plane, you can able to get third peak. So depending upon if in thin film if different grains are there, so that structure you can able to identify if you have this, you can varying this area of that penetration depth of this X-ray beams inside the samples. So here if you see the instrumentation part, you have a source that is here is X-ray source is kept here, then the X-ray source, the X-rays will fall on the mirror, and then it will come to the sample. So after sample here it will go to the flat monochromator, and then you have a detector here. So you can able to so by your sample rotation is possible, changing the sample rotation with the grazing angle variation, angle of incidence you can vary, and you can able to easily get the different depth profiling you can able to get. So you can see an example here that the normal X-ray, conventional X-ray, and grazing angle X-ray. You can see the bottom that is this one is mainly from a conventional X-ray 2 theta couple scan. You can see the peak here is very low, but that is a TiO2 photocatalyst. You can see with thin film with grazing angle incidence, so you can able to see that peak is quite high. So that is mainly that when you have a conventional like powder, you are a conventional thin film measurement you do in a conventional XRD. Here in a conventional XRD, if you do with a thin film, your penetration depth will be and if you do with a small angle, you can see the penetration depth, your area for study is quite large. So X-ray is mainly located inside the thin film, it did not go to the bottom substrate, so you'll be able to see these peaks more clearly. The right side image, you can see that a solar cell image, there you can see that at this type of peak, copper, indium, those peaks are absent in case of see when you have a theta 2 theta, these peaks are absent here, but when you go for omega, the thin film 1 and 0.5, you can see these additional peaks that you can able to get. So similarly other peaks are also you can able to see. So in normal XRD, a large portion of diffractogram comes from the substrates, like in diffraction. So the X-ray beam can pass through the thin coating, it will go to the substrate. But in case of grazing angle XRD, so it's mostly diffraction, that area of interaction of X-ray with the some coating will increases. It's mostly avoid that going into the substrate, so you'll get better resolutions. So you can see another example here of the solar cell. You can see that the molybdenum substrate on that CIGA solar cell and top surface is zinc oxide. You can see was varying the this angle, that the grazing angle you can see 0.45, 1 and 2. You can see how this peaks are in the additional peak are getting, and then how that intensity of that particular peak is increasing depending upon your other peaks information you are able to get in each set. The depth profiling, this is mainly by varying the incident angle. Whenever incident angle is very low, here 0.45, that grazing angle you can see only on zinc oxide surface it is there, so peak related to that you are getting here. But whenever angle grazing angle is equal to 1, you can see here is going to the CIGS there, so additional peaks are getting. When you go for omega equal to 2, you can additionally go on the further detail the molybdenum surface, you can able to go, you can see that peak here. So this type of depth profiling can be done by using this thin film XRD, grazing angle XRD. Another example here I have shown that this is a intermetallic structure. You can say the top surface titanium nitride, then titanium carbide, again titanium nitride, and tungsten carbide with the bottom substrate. If you go from the here to here, you can see this region I have selected. In that region, see how the titanium and titanium nitride and titanium carbon, titanium carbide are overlapping each other. You can see here it is completely titanium nitride, and then this is the diffuse zone where nitrogen can diffuse to the other layer and carbon can diffuse to here. So you have a zone here, and this zone information if you want to see by depth profiling, you are able to see this structure by using grazing angle XRD. You can see here this is a complete titanium nitride. When you have a titanium that angle is 10 degrees, that higher angle, you can see that the top surface information is here, and that is, you are able to get the titanium nitride peak you are getting, and that titanium carbide is very rich there. So when you go inside that depth profiling here, you can see how the nitride peak intensity is from here. This is the angle to 2 degree, that is the very low angle here. This is the substrate, and this is the thin film on this surface, and you have a angle is very low, 2 degree. You can able to see here that is mostly titanium nitride peak is there. When you keep on increasing the angle of incident, like then your penetration depth if it increases. So because of that, you can see that how this peak is diminishing, and this additional the TiCN peak, that those peaks are intermetallic, the structure in between structure TiCN is producing, and then when you go little deeper, here TiC peak is able to see. So you can able to see the intermetallic structure like in using this type of X-ray technique. Here you can see the residual stress. You can also measure stress or orientation. You can see here it is a on-straight sample, and then due to the tensile stress, that if you stretch it in both sides, how the planes are elongated because of the stress. You can see that here without stress, this one is without stress first peak, and the second one that is with stress. You can see how the peak is getting shift. Sorry, the unstressed is the black one, the second one is the unstressed, and the level 1 is stress one. Because of the stress, this is a tensile stress, because that is a angle shifted to lower and peak shifted to lower angle. If it is compressive, so it will shift it to other side. So residual stress, that the peak position shifting you can see, and even you can see the bismuth titan example that they are grown on a strontium titan substrate. You can see these are highly oriented 004, 006, 008. So all are 00 L peak you are able to see. So 0010, 0012. So all these, only one type of peak you are able to see with a highly oriented structure. Those things you can see by using this. So like single crystal X-ray, this thin film X-ray is extensively used for characterizing, the thin film structures by identifying their phase, as well as, to identify the, depth profiling. By through depth profiling, you can easily identify. So you can identify them by using intermediate structure, like whatever the intermediate structure forming between two layer or multi-layer structure, or even like the solar cell, all this thing information correct, and that you can identify using that thin film XRD. So in the thin film XRD, single crystal, and this powder X-ray, they use X-ray source as mostly you have a tungsten filament there where X-ray as that electron are produced, and from a harmonic emission electron are falling on the tungsten filament, and then you are getting that X-ray copper K alpha, or other things. So here the source is mainly used as a harmonic emission there, but if you use in a kind of synchrotron radiation where high energy synchrotron XRD, so there the radiation source is high intense, and because of that, what are the information more, you can get more information than the normal conventional XRD. So that we'll discuss now. So if you go for a synchrotron XRD, so first of thing you need a synchrotron. That is nothing but synchrotron see is a ring which uses magnetic and magnets and electrodes to accelerate the X-ray. So here you can see these are the rings here, these synchrotron rings where X-rays are produced inside this, or light to nearly a speed of that. The acceleration speed of that X-ray is about the speed of light, and then when it passes through this circular rings, so it will accelerate in each step, and you will be able to get a highly energetic X-ray that you will able to see here. The synchrotron radiation is an advanced polluted light source with high intensity. It is very high intensity. You can see the synchrotron X-ray produced X-rays that are monochromatic of very high energy and short wavelength, a right energy for light element. You are the carbon, oxygen, those type of element you are not able to see in normal XRD. Even those things you can see using this synchrotron radiation. Here you can see that different point things I identified. One, you have an electron ground here, one, and then you have a linear accelerator. So that and a booster, that three, and then your storage ring, that X-ray or electron will be stored here, and then it's a end station where it's come out and you can use your analysis here. In addition to the conventional diffraction technique, it also enables atomic pair distribution, that PDA pair distribution analysis. Even in amorphous material, you can able to see that both sharp and diffuse scattering that generally happen in amorphous material. So by analyzing that pair distribution function, you can easily identify the structure of the compound also. So thus enabling one find to bond distance and coordination number, you can also find out that are not fully non-crystalline material are able to find out that information. And synchrotron XRD has many advantages in structural characterization material on atomic or molecular scale, or even you can use as a very trace element. Like I told that that if you're doping something on this material is on copper of zinc oxide, so even copper concentrate is less than 0.1%, the detection limit is very high in case of synchrotron XRD. So the main characteristic of synchrotron XRD is mainly due to that high intensity is mainly to high brightness, one thing. So brightness with the brilliance of X-rays from third generation source is about 10 to the power 5.12 times more intense than that of laboratory source. So up to 10 to the power 5 to 10 to the power 12 times higher intense, which means the time required to record the diffraction pattern is significantly reduced. And then the resolution is much higher and is highly collimated. The synchronous light is parallel and therefore it's spread minimally as it propagates. So its spreading is very less. So you can get highly collimated beams and it's a wide energy spectrum. So the radiation include wide range of energy, infrared from infrared to hard X-ray. So allowing the optimal wavelengths, you have a tunable wavelength that you can choose here, like in case of copper K alpha or molybdenum that is fixed. So here you have a variable in wavelength and reduce the absorption either in sample holder or varying that you can vary the wavelength experiments. So you have a short pulse time structure. You can see picosecond pulse time, picosecond level pulse length allows you resolution, process resolution, time scale that can reduce to higher penetration. It's a high intense, high brightness. That means the penetration depth is greater than the laboratory conventional XRD. So that will improve the possibility of both time result and high resolution in situ experiment can be done here. If you see the optics of synchrotron X-ray, you can see here you have a synchrotron source that is here. From there, electron is coming out in falling and collimated mirror, and then it's through the slit in focusing crystal monochromator here, and then focusing mirror in the slit will finally X-ray will produce somewhere here, then X-ray will come and fall in the samples here. So in synchrotron radiation, the beam line refers to the instrumentation that carries synchrotron beam. This is the whole thing in the beam line from that carries synchrotron beam to the experimental end stage. This is the end station where experiment is done. From here to here, it's called synchrotron beam lines. It incorporates like monochromator, slit, mirrors, other devices to select appropriate wavelength and focus is there. So here the sample is mainly aligned by capillary geometry, the most common applied geometry for synchrotron radiation, like a small capillary or sample is to mount it in the capillary and then X-ray fall on this and you will get diffraction pattern. So because of highly monochromatic, high flux and highly collimated, synchrotron possesses many advantages like K alpha 1, like K alpha 2. So that can be separated by mostly using conventional XRD. So like though your K beta you separate through nickel using some filter. For copper K alpha use nickel filter. So but here that K alpha 1, K alpha 2, so no K alpha 2 peak diffraction peak is here. So that you can because of highly monochromatic and high signal to noise ratio, you will get better data and high angular resolution. So this allows analysis of complex structure, the refinement and observation of complicated peak broadening effects you can easily identify by using synchrotron XRD. When combining with synchrotron XRD with its newest, ultra fast efficient solid state detector, where solid state detector you combine with this synchrotron XRD, even 0.1 weight% is the detection limit. So you can able to get very low per concentration of dopant. You can see whether there is any secondary phase or not. So which you can't identify in conventional XRD. That is possible here with a sample of few microgram of powder sample you can use for this study with high accuracy. Then sample should be finely uniform, it's grounded, and particle size should be less than 20 micron, so that then loaded to a 1.1 to 0.5 mm glass capillary. Since sample is loaded to the capillary tube, so it is to finely grind, and then you can be mounted on that. So both in situ and ex situ experiment is possible. Like during some reaction is occurring during your heat treatment or your pressure, so those can be done with the synchrotron radiation as well as ex situ X-ray. If you see here, here in example that laboratory XRD, that is red one, and synchrotron is black one, you can see that if you see the difference, you can see in the red one, you can see how this laboratory XRD, the intensity of this molite and anhydride. So those were quartz, these two peaks are very less intense in case of black one. You can see here these are quite low intense, but when you go for high that synchrotron XRD, you can see in the black one. Here it is less in the red one. In the black one, this is quite highly intense. You can see the intensity is much high in this case, and also the other peak intensity, like see the calcite here. The calcite here, it is not almost little bit, but you can see the black one when the synchrotron radiation such a large peak you can able to say. In magnetite, which you can see here, so these are the ash sample. In the ash sample, different what are the components are present, so those additional information you can able to get. You can see all those information you can able to get here. So diffraction peaks obtained from single synchrotron XRD are stronger and more well resolved than those from laboratory XRD, especially for a minor phase such as magnetite. You can see this is a magnetite, a small phase, so that magnetite you can able to see here in case of this synchrotron XRD, that was not clearly visible in case of conventional XRD. So similarly, that as I told, in situ experiment, you can see the temperature dependent synchrotron XRD. You can see at 300 to 600 starting K, how their particular peak at about 16 to 17 degree here. You can see the highly intense peak. You are able to see that the particular phase is growing. So because of that, for phase formation, you can able to see the additional the growth in particular direction, or as additional phase that can be seen. You can see this is an example of lead, lanthanum, titanium aluminate, ceramic, that X is varies 0.09. You can see XRD pattern of different temperature, and then this you can see that here this one you can see the one information of 300K, two peaks are there, 001 and 100, and then these peaks two are merging, and finally we are getting one peak. So that orientation in particular one direction, those information you can see. And if you have a rising temperature, if you have a tetragonal to cubic transition, that C by A ratio, if you see the lattice parameter, how that C is decreasing and A is increasing. So from that information, lattice parametric information, you can able to see the different phase formation. So here X-ray, that energy is higher than 5 keV is used. It can be beneficial for in situ experiment. So very high energy X-rays are used to this. Similarly, like if you have a system that undergo pressure dependent phase transition, so you can change the pressure from 0.3 to 25.9 gigapascal. You can, by changing the pressure, you can see how the peak is shifting to from here to here. That peak is shifted, and then how the intensity of the peak is varies. So hexagonal here, the phase structure is gradually the hexagonal phase structure is gradually shifting to a peak to a larger angle. You can see here is a lower angle, so peak is shifting, increasing the pressure. When you have increase in pressure, indicating the lattice, shrinkage upon compression. So because of that pressure, so lattice is compressing. So that type of information from the peak shifting, you can able to identify. You can see how the A parameter, C parameter, they are changing with experimental and fitting calculation. You can able to identify the pressure dependent structural changes. So if you combine the diffraction, like in case of synchrotron XRD, so there is a possibility you can, in addition to X-ray diffraction, you can combine other technique to this, and then you will able to image also, or you can use combine with a spectroscopic technique to this. Like for example, you can combine, like at present it's possible to carry out synchrotron XRD experiments simultaneously with combined with collection of Raman spectroscopy or X-ray absorption fine spectroscopy that we will study now. So X-ray absorption fine spectroscopy, so that can be combined with the synchrotron XRD, so you will get better informations. So the mapping of chemical, physical, and crystallographic properties to the sample in 2D and 3D using smart combination of diffraction, imaging, and spectroscopy, it can be possible with using synchrotron radiation. For instance, like you can use simultaneously energy dispersive time results, EXAFS and XRD applied to observe, how thermal evolution is occurring in case of magnesium boride, hydride, and niobium oxide. So those type of complex mixture you can able to identify more information by using combined techniques. So here that one technique that mostly used for in addition to synchrotron XRD, that X-ray absorption fine structure EXAFS. So X-ray absorption near structure, like the subunit of that is X-ray absorption near edge spectroscopy EXINAS, and extended X-ray absorption fine structure EXAFS, commonly done with synchrotron X-ray radiation because of high energy X-ray yield, more precise data. So in addition to the XRD, the synchrotron XRD data, is able to get absorption spectroscopy data. So this absorption spectroscopy data and fluorescence spectroscopy will discuss after 5 minutes. We'll take a break here for 2 to 3 minutes, about 3 minutes, and then we'll So if there is any questions on so for X-ray diffraction techniques, so you can raise some questions. Otherwise, we will discuss X-ray absorption spectroscopy. So, okay, then we will start X-ray absorption spectroscopy and fluorescence spectroscopy. So, X-ray absorption spectroscopy, I will discuss two parts, mainly EXNES and EXAFS. So, if you go for X-ray absorption spectroscopy, like whatever X-ray diffraction, there we are discussing with the diffraction patterns and how the X-ray, the diffraction that the X-ray being diffracting by satisfying the Bragg's law. Here in X-ray absorption spectroscopy mainly deals with absorption related things. So if you see the intensity of X-ray beam passing through a material or given thickness X, if a material here, the thickness is X. So you will determine absorption coefficient is C I equal to I0 into e to the power minus mu x. So mu represent here fractional linear attenuation coefficient, or you can express also mu by rho, that is mass absorption coefficient. So this mass absorption coefficient mainly determines so the main absorption spectroscopy main things that behind this absorption spectroscopy. Here that the fraction linear coefficient that depends on X-ray energy, how much energy E you are applying, atomic number of that particular material which you are scanning, and then density as well as atomic mass. So mu is equal to rho z to the power 4 by A e to the power 3 here. So X-rays are here absorbed to the I discussed the photoelectric effect there. So in that case, so incoming X-ray photons is falling on the sample, then some electron is knocking out from the core, so that you are getting a photoelectric effect. So here the X-rays in X-ray absorption spectroscopy, X-rays are absorbed through the photoelectric effect here. If you see here, the absorption occurs when incident X-rays are energetic enough to remove core level electron from an atom. So you have a core level electron here, and you can see the KL M cell of post atomic model. You have a core level electron, like you have a at 1s, 2s, or 2p1 by 2 or 2p3 by 2. So there are different levels of energy. The electrons are there, and you have X-rays coming, and that X-ray which is energetically enough to remove this core electron, then only absorption will occur. So excitation of core electron here, from the core electron will excited from the ground state. You can see here that core electron will come here, it will go to here, it will excited state, higher unoccupied states that below the ionization potential or unbound state. If you go beyond this, we have a going out of this continuum, like out of this element. So before that, there is a vacant orbitals, like unoccupied energy states here. Those are continuum unbound states. So electron moving to that side. And this is extremely sensitive to chemical state and local environment. Like you have a +2 charge, +3 charge, nickel +2, nickel +3. So there will be a huge difference between this type of, because depending upon the chemical state, your absorption will change. You can see if your absorption of the electron is from K cell 1s 1 by 2, then that electron is jumping from the ground state to the here, the outer of the core electron going to the unoccupied state, then it's the K edge is called K edge. If 2s 1 by 2 is going out, it's called L1 edge. If 2p 1 by 2 is going out, it's called L2 edge. So 2p 3 by 2 is L3 or stay edge is called. So these are unoccupied state where these electrons are moving. So if you see when necessary energy E, binding energy, so moving this. Yeah, so to moving this electron here to this position, so you have to overcome the binding energy. If you have the necessary binding energy for a core electron transition is attained, the mass absorption coefficient increases sharply in causing an absorption edge. Like you have a K cell here that once your binding energy coefficient is up, binding energy is up, your X-ray energy is approaching to that binding energy, then what will happen that the electron will move from one state to the other state depending on K or L cell, and then because of this movement that the mass absorption coefficient will increase sharply. You can see here the mass absorption is increasing here, and similarly at L state this is increasing here. So that the absorption occurs when you have a changes in that band, that necessary energy of the core electron transition rejected, you will see the mass changes in mass absorption coefficient, and that is causing absorption edge. These edges, each edges occur at its own critical absorption. Like if you have a K cell, L1, L2, L3, they all have a different absorption edge. Like for example, if you see iron, that 7.1 kiloelectron volt is the K absorption, whereas that nickel it is 8.3. So depending upon the element, their K or L cell absorption edge is different. So that absorption is different. So that means like characteristic X-ray, this absorption edge are these are specific to the particular element. So EXAFS is an element specific technique. So you can identify each element depending upon the absorption edge. So information what you can get from here are bond length, bond strengths, the nearest neighboring atom, or defects, disorder, those things you can able to find out. It's like nearest neighboring information that you can't get in X-ray diffraction technique. So here that though bond type, bond length, and all these things you can get in single crystal X-ray, but in case of X-ray absorption spectroscopy, you will able to get near neighboring atom distance and disorder, those information you can get. So edges are labeled according to the cell from where core electron is generating, whether it's generating from K cell, then it's called K edge. If it's the L cell, that's L1, L2, L3, depending upon whether from 2s or 2p1/2 or 2p3/2. So if you see the X-ray absorption spectroscopy, so that's it divided two parts. That is one is EXAFS and one is edgeness. So that X-ray absorption fine structure. So this is simply by modulation of X-ray absorption coefficient at energy near and above X-ray absorption edge. Like for K cell, you are getting an absorption like this here. So here this is the absorption zone here. That this is the near absorption energy near and above absorption here. So if you see these 2 points, that like you can see from here this level to this level, this is before absorption, then its absorption occur here, then it's after absorption. So if you see that difference, the modulation of X-ray absorption coefficient at energy near and above X-ray absorption edge, that is gives you X-ray absorption fine structure spectroscopy. So this is mainly core electron that propagates outwards at a spherical. You have a electron here, core electron, that electron, the wave vector of that electron, it propagates as a spherical waves as per the de Broglie equation. It spreads, and that wave factor K for that particular electron K equal to 2 pi by lambda, or if you put this equation, 2 pi p by h. So the kinetic energy of that particular X-ray will be Ek, you will half mv square, you will run with 3h pi by 2 pi k square by 2m. And kinetic energy Ek equal to E minus E0. E0 is the threshold energy, that amount of energy of the photoelectron needed to promote the electron to the continuum, so that the minimum energy required. If you incident beam is h nu E, so that E kinetic energy equal to h nu minus E0. And if you combine this equation, you will get a wave vector equation K equal to square root of 2 pi by h whole square 2m into h nu by E0. If you see, so this factor is almost constant. Only thing which is depend on h nu and E0. H nu is the photon energy, that your X-ray energy you are imparting on the sample, and E0 that the threshold energy, that is the amount of energy the photoelectron needed to promote the electron to the continuum. So if you see here, like your spheric is going through a spherical waves. So once X-ray coming here, that X-ray is also you interact with this core electron, and that wave will propagate like this. So you have a spherical wave of that particular electron, and then because of interaction, you will get interference with the neighboring atoms. Like another atom here, here is another atom. What will happen? So wave generating from this direction will interact with this electron, is generating this side. It will interact with this electron. So you'll see an interference of this. Since EXAFS is an interference effect and depends on wave nature of the photoelectrons, it is convenient to think the process in terms of photoelectron and wave vector rather than energy. Like in earlier case, you generally talk about energy, but here, since it is an interference technique, X-ray absorption technique, so it deals with mainly that photoelectron wave vector rather than energy. So the wave vector is the most important parameter here, how the interference is occurring in this case. If you see here, if you see the EXAFS, you have two subsets, that one is EXNES, one is EXAFS, that here. So if you see here in diagram, you can see you have a core electron here, that is the X-ray is falling here, then your electron is promoting from here to the unoccupied cell. K. If you are going to K equal to 0, the low energy EXNES here, just enough kinetic energy to able to escape the electron to the continuum. So from here, it goes to the unoccupied state. So here you have a multiple, while this electron going to this here, it go through multiple scattering process between multiple surrounding. And you see, you have a surrounding atoms here, so this atom will interact to go there. So that is one interaction here. There is possible here, but if you have not enough energy, so for this EK is enough, then you will able to interaction, you will able to see. But if you have a low energy, like just a continuum energy, then what not enough energy to completely leave the atom. So here electron will come out from here and it will stay here unoccupied state. But here when you have a kinetic K less than Kc, that low kinetic energy and high kinetic energy 2K, you can see electron is just going out of that continuum state. If a high, very high, it go much higher side. So you will get your EXAFS here, EXNES here. So EXAFS is a low kinetic energy. Kinetic energy is just enough to overcome that barrier to move from here to the unoccupied state. There are multiple interaction will be there with different atoms. But in case of very high K, the weak backscattering occurs. So single scattering here this will directly go out. So there will be single scattering process between only one neighboring atom. So what is the nearest neighboring atom? With that it will interact instead of interacting with these elements. So if K equal to 0 in this equation, so low energy X-ray absorption mainly will give a near band edge structure because of this electron jumping to here, but it's not completely going out. So but in case of K lies between 0 to 2 by R, that R is the distance between the observer and the scatter. This is the atom, so this is one atom, this is another atom here. So this is the scatterer, from here it will scatter, and this is another atom, that is the observer. So distance between this is called R, that is the nearest neighbor distance. So if it is in between 0 to 2 by RK, then you will get EXNES. You will get this type of EXNES spectra. When you have an extended absorption fine structure EXAFS, you will get when Kc is equal to 2 by R is going much out. So you will get extended absorption spectroscopy. So if you see first EXAFS, that the absorption of a free electron, if you see this is a observing atom here, then what will happen? There is only one is here. So then X-ray is coming here, falling here. Then what you will see? You will see a photoelectron is moving, and then you will see corresponding wave vector propagating like this. So here what you will say, because of this single electron, you will see there is a band edge transition from ground state to this E0. If you see absorption probability, so it will increase like this. But it's isolated atom, mu is with sharp step at the core binding energy and is smooth as a Fe function. That means because of this isolated atom, so there is a sharp transition you will observe here. Once E is large enough, that this will occur once E energy is large enough to promote the core electron to the continuum, there is a sharp increase in absorption. Because here to here it will go to the excited state, then what will when the absorption will occur. So here the single like isolated atom, you will see this type of spectra in case of atomic absorption, X-ray absorption spectroscopy. Here atom absorbs the X-ray energy E by destroying the core electron of energy E0 and creating a photoelectron that has energy E minus E0. So here in that you will get in a single this type of pattern. But when you have a neighboring atom, you can see here there is a blue atom and a red atom. The wave vector generating from blue atom interfering with that of the red atoms. Then because of the two observing, there is this is the observing material atom, is the scattering atom. Then what you will see there is a whole interference between the wave vector of both two. So in that case, in addition to the absorption edge, you will see some additional spectra you will see. So that is called mostly extended absorption spectroscopy you will see. So with another atom nearby, the ejected photoelectron can scatter from the neighboring atom, and the backscattered photoelectron will interfere with the itself. So when it's scattered here, so that the backscattered photoelectron that will interfere with itself. So there will be interference between the wave vector. So the amplitude of the backscattered photon at the observing atom will vary with energy E, causing an oscillations in the absorption edge. So once you initially are getting a sharp absorption, because of this interference, what you will see a oscillation type, causing a oscillation because of the absorption edge. So EXAFS is an interference effect of photoelectrons with itself due to the presence of neighboring atom. So because of this, you will be able to see the neighboring atom distance between two atoms in a structure. You can able to see, measure the neighboring atom distance. You can easily find out the bond length. So if you see here that X-ray absorption spectrum, here you will see the absorption coefficient versus energy. Initially you can see there is a sharp edge, and then there is oscillations. So the sharp edge before is mainly pre-edge or edge. You will see that it will give you electronic information, and then that EXAFS will give you geometric information. The shape of the edge and the pre-edge, that this is the pre-edge before going to the absorption. You can see there is a small peak here, that is pre-edge peak, and then you have an edge peak here. The sharp edge and pre-edge resonance are characteristic of the local symmetry of the atom. This is mainly see that local symmetry of the atom. This will give electron information, and they can be used as a fingerprint to identification of its local structures. An analysis of photoelectron scattering by surrounding atoms near and above the core level, above the core level here, the interaction, so that though it's a short range interaction, so that can be identified. So X-ray absorption pre-edge extending a few electron volt here to here, it shows in a few electron volt below the absorption edge. This is the X-ray absorption pre-edge region, and above the region is above this absorption edge determine the local density of the vacant state of the observing atom. So from there you will get the geometric information. The region is very sensitive to the valence state. You can able to identify the oxidation state like chromium +3, +6, or iron +2 or +3. Those type of this oxidation state, the valence state, you can able to identify by using this X-ray absorption spectroscopy. So as I told, the EXNES and EXAFS. EXNES is this is a neighboring atom, the multiple electron interaction here. So region from 30 to 40 electron volt here. You can see here, this is the energy band, this is the band edge is here mostly. So 30 to 40 electron above, you will able to see here this to this region, this the EXNES area. Whereas beyond this, here to here, you will able to see high energy state. The past edge, this 42,000 electron volt past, you will see to EXAFS. So it's a low wavelength, long wavelength electrons in case of EXNES, but here it is a shorter wavelength electrons EXAFS. But here in EXNES, you have multiple scattering is possible here, but in EXNES you have a single scattering is there. So you can able to find out the nearest neighboring local symmetry by using the from EXAFS study, whereas coordination number and band structure can be identified from EXNES, like whether it's a 12 coordinated, 6 coordinated, or tetrahedrally coordinated or octahedrally. So those type of coordination information you can able to find out on EXNES. Whereas EXAFS, you will see the intermediate bond length distance between two atoms. So those type of structure you can able to see. So from this multi-electron, you can see the EXNES. Here you have a photoelectron from atom A green being scattered by two neighboring atom, blue and red. There is a blue atom and a red atom. Then the wave factor is coming from the green atom. It's interacting with the other two. The circular ring represents the constant phase wave fronts, so that whether the wave front is coming from the one particular atom, it interacts with the other atom. So here the kinetic energy equal to X-ray energy is equal to energy of X-ray minus energy of binding energy. Once it overcomes binding energy, then only electron will come out, and you will see the absorption edge. So less kinetic energy means longer wavelength. So long wavelength means you will get interference dominated by the multiple scattering. If a long wavelength region, so you will have many neighboring atoms there. Therefore, multiple scattering paths have to be considered. So there is a scattered from this side, there is scattered from this side. So you have to consider the multiple scattering. However, multiple scattering makes near-edge spectra sensitive to the symmetry or neighboring atom arrangement. So you have a neighboring atom, multiple atoms are there, so you can able to see how they are interacting to each other, and it can be used as an indicator to find out the bond symmetry, such as tetrahedral and octahedral geometry, and this makes an indicator of valency in the certain systems also. And also it can be used for electronic band structure calculations, since band structure calculation also involve multiple scattering of electrons. So you can able to get information about band structure, symmetry, and as well as oxidation state by using this H-ness. So in case of EXAFS, you will get information about that neighboring atoms only. You can see here the photoelectron from the atom green is being scattered by the neighboring blue atom. If a wave vector of the green atom, it's scattering back from the wave vector from that of the blue atom. So there is a direct single interaction here instead of multiple. So here the increase in electrokinetic energy results in photoelectron with shorter wavelength. And then this EXAFS, as I told, amplitude is proportional to 1 by r square, and the other factors such as inelastic loss, thermal fluctuation, mean free path that also contribute to this here, and multiple scattering significantly that affects this information. For this region, scattering is most limited to atoms or ions in the vicinity of observer, like when you have within a distance of 0.5 nanometer. So this EXAFS information you will get. So since a multiple interaction will interfere, so the shorter length can be possible. So here this can use for phase and amplitude of the scattered photoelectrons depends on the factors such as whatever because of that interference of the both the observer and the scatterer, you will get information about the bonding atoms, any change in surrounding potential, like you have a nitrogen atom, you replace to oxygen, then if the carbon, nitrogen, carbon, oxygen, so those type of changes, that information you will be able to get, and you can get to de Jaeger's, de Jaeger change in surrounding potential due to the de Jaeger initial and final state, that information you can find out. And thus numerical analysis of EXAFS information about the intermediate local environment surrounding an observer ion. So you can get information by just local environment of that particular observer atoms. So, but the analysis of that EXAFS or EXNAS is little complicated. So first, once you get the absorption spectra, you will get this type of absorption spectra. There is a pre-band edge, then there is a sharp band edge, then the oscillation you will get. So what you have to do for the EXNAS data, first that pre-edge data is here. You have that's like a background. You have to subtract your pre-edge from this. Once you subtract the pre-edge data, you will get a symmetric like post-edge subtraction. So you'll get this type of spectra. That's mu0 E, that oscillation you will get. So after that, what you have to do, isolate the EXAFS from oscillations. So whatever the isolation of the EXAFS data, that you have to remove from all the oscillation, you have to remove, and you will get that EXNAS spectra you will get. And then you can go for a first derivative to find out that E0 is the maximum of the first derivative. Once you find E0, you know the H nu, that is all other parameter constant. H nu is fixed, that depend upon the X-ray energy, and E0 you know from this first derivative that E0 is the maximum of first derivative. So here, then what you will find out, the K. So once then you can use this type of software, that is Fourier softwares, that you can able to find out that fitting, which can get EXNAS data you will get, what the information you will able to get. You can see the information after subtracting, you are getting this type of spectra. Then you can see in case of this is chromium plus 3 and this is chromium plus 6. In chromium plus 3, you can see this is here tetrahedral coordinated 6 plus and plus 2 plus 3 tetrahedral coordinated. Those type of symmetry, coordination symmetry you can find out. In case of chromium 6, so you can see there is a strong absorption edge here. Wherever it's case of chromium 3 plus, this absorption edge is missing. We are only getting these two peaks. So it's can show the dramatic dependence of the oxidation state and coordination chemistry. And for ions with partially filled D cells, if you have a partially filled D cell, there will be possibility of P and D hybridization that changes your octahedral distortion or tetrahedral very large tetrahedral coordination, those type of information, how the PD mixing is helping to the changes in the octahedral or tetrahedral geometry, those information you can able to get from this Exnes study. Mainly oxidation state is the more information that you can get here. You can see here is a calcium chromate and it's the chromium metal. So you can see in calcium chromate is a tetrahedrally coordinated. Here there is no, it doesn't have an inversion center. Since it doesn't have an inversion center, you are able to see that band edge peak is here because of dipole allowed transition of 1s electron to the 3d orbital. Because of the transition of 1s electron, you can able to see a band edge in case of calcium chromate. And when you are going to chromate to chromium oxide, you can see in the case of chromium oxide, this band edge is almost, disappear. We are only getting two small peaks here. So that is mainly that exhaust of chromium Cr2O3 or chromium metal, where chromium is located at the crystal side, and that is at the inversion center, the side at the center of inversion. So pre-edge is completely disappear, and it is built up with the structure of corundum structure with octahedral geometry, and this octahedral symmetry or the spectra is recognized by two small. This is two small absorption, one here and one here. You can able to see that assigned to the transition of 1s electron to the anti-Bernoulli octahedral symmetry. And then in case of chromium metal, you can see that this oscillation peaks you are able to see, but your band edge is completely absent. So oxidation state is the changes from here, so that can able to see by using this type of Exnes spectra, both coordination oxidation state and coordination number. But if you go for Exap's analysis, and that is little more complicated than Exnes. So from this equation, k equal to square root of 2 pi whole square to 2m h nu minus E0, then you have to find out this wave vector k function of that Fourier transform. You have to do first Fourier transform from R space, the k to real space you have to transform from wave vector to real space you have to transfer by using this equation. Then by using model fitting, you will amplitude that here you can see the amplitude fk is there, and there is a phase shift, delta is the phase shift, the lambda is the how the free mean free path. So all this terminology has to come into picture, and then the distance of atom, R coordination number, mean square disorder, all these things you can find out from this. So here that the amplitude and phase shift here depends on the atomic number. So if a high jet material, it's different, a low jet material is different. That is exact sensitive to jet of the neighboring atom. Like one atom is wave vector is going like this, another atom wave vector is coming here. So it depends upon both the jet value of these atoms as well as this atom. So mainly that is sensitive to the neighboring atoms here. So you're able to get more information after this analysis. So here you can see, just I've given two example here. The Exap's analysis available for reduction or fitting from Exap's, that you can see that equation. Initially you have a Exap analysis first convert to mu E versus E data to phase data. You have to convert this amplitude to phase data. You have to convert from AF to phase data. You have to convert. So you can see that this is mu E versus E photon energy, how that oscillation to photon energy that is converted by this equation. You have to find out minus, if you know mu 0, that's the best background, and then you will find out. And then by this is to convert it to kx that wave vector photoelectron wave number defined k in this equation. You would convert to k. Once it's convert to k, then only you will be able to get this type of spectra. So if you more like here is k square versus k wave vector square, so you will get this type of oscillation. And finally k versus k data is a Fourier transform to derive R, the real space versus R spectra. So generate theoretical lecture spectra. You can now you can find out from this the bond length, all this information you can find out by bond distance R, coordination number N, disorder factor, all those parameters you can identify it. Here you can see that this is the ZNO structure and this is manganese doped with ZNO, dysprosium doped with ZNO. Because of the doping, how the spectral changes, and from that you can find out the bond length. So this to this distance you can find out that the ZNO distance is 3.84 angstrom. When you have a zinc distance, it's how much, zinc oxygen distance is how much. So that from the peak, from the position of the peak, you will be able to find out those, this ZNO bond length is about here, and ZN bond length, all those information you'll be able to find out the near neighboring atom distance. So this EXAFS is mainly related to the photoelectron spectroscopy, like that we have. Once you have a sufficient kinetic energy you applied, so because of that kinetic energy, so electron will go from the ground state to the continuum, and during that process you will see a bandage changes, and that bandage information will give you both EXAFS and external. Because of the, if there is a single atom, you will get only bandage. If there is a multiple, because of that, then there is a oscillation between, because of that two wave factor interacting or multiple wave factor interacting, you will get information about the oxidation state, coordination number, symmetry, all those information you will get from X-ray absorption spectroscopy. So like X-ray absorption spectroscopy, there is another technique called X-ray fluorescence techniques. So in X-ray fluorescence technique is mostly used for identifying the XRF, which identification of elements. So that we will see how the X-ray fluorescence technique is used. So if you have a principle is almost similar here to X-ray absorption spectroscopy. The excited core level, in X-ray absorption spectroscopy, the core level is going to the continuum, and then that bandage thing, that absorption things you are measuring. That case here, the excited core level here, it goes to the instead of continuum, the higher on field 3D orbital or something orbital, and then what will happen? And this core, this electron, that excited core hole will relax back to the ground state. So this electron again come back to the ground state by transition of higher level electron into the core hole. So because of once it goes out, so then higher level electron, so those electrons will come to the ground state. Since core electron is lower energy position, the excess energy is emitted. So here is called fluorescence X-ray. Like here X-ray is falling here, then this electron is going out, and because it's a vacant side is creating, and that vacant is filled with a higher energy orbital. So the electron from 3D is coming here, but this energy of this particular higher energy is higher than this lower one. So the excess energy that is released as a X-ray fluorescence. So the energy of the fluorescent X-ray is the characteristic of the observing atom, of the particular atom which is observed and detects a go to excited state. It depends on the fluorescence characteristic to that specific, to that element. So you can be able to use both qualitative and quantitative measurement using these techniques. So if you see here, this also follows, Bragg's law here, the X-ray diffraction. First you have a specimen here. Here is the specimen with X-ray tube. From here, X-ray diffract from the sample and goes to a analyzing crystal. This analyzing crystal is here. That analyzing crystal rotates to reflect each wavelength to satisfy the Bragg's law. So this analyzing crystal, so once it falls here, X-ray fluorescence will be generated, and that will go, that X-ray from the specimen, the fluorescence will come to the analyzing crystal, and from analyzing crystal, it goes to the detector to wherever it satisfies the Bragg's law. So that analyzing crystal rotate so as to satisfy the Bragg's law, and detector measure the position and intensity of that particular peak, and you'll able to see this type of spectra. So where you can able to see whether it is come from nickel K, like K alpha, K beta, that can be identified in this. So XRF is diffracted by a crystal at different angle to separate, the X-ray of different wavelength. So depending upon the element, so your that wavelength will be different. So since X-ray fluorescence characteristics of a particular element, so you're able to identify that particular element. So here the two types of detector are used. One is energy dispersive X-ray, another is wavelength dispersive. Like energetically you can differentiate each what are the elements, or you can by wavelength wise you can differentiate, so that you can see detection analysis possible, energy dispersive or wavelength dispersive. And here element analysis is possible, and without don't need any crystalline material in amorphous material. It is a non-destructive and fast method to identify the particular element. In EDAX, as I told, it separates X-rays according to the energy, or as do wavelength, WDXR which wavelength. So energy dispersive detector is combination of a multi-channel analyzer. Here is sequential system detector is placed in a fixed position, so each wavelength wise it separates. So all elements in the samples are simultaneously excited here, that can be identified energetically. Here X-ray are directed to the crystal which diffracts the particular wavelength wise it separates. However, the Bragg's law is satisfied, so wavelength wise it separates. So here in case of EDAX, the X-ray the energy dispersive detected without being separated. So each wavelength is not necessarily separate here, but here you have to separate the wavelength wise, and that is the difficult part, but using double DS when able to identify the chemical. Even all elements except hydrogen, like all except hydrogen, helium, lithium can detect by this XRF. So the all higher element that Z value more than lithium, you can identify by X-ray fluorescence techniques, and here you can see detection limit is about 0.1%. So here you have a K, L spectra, and those things you can find out. And if but here in quantification, like this is a milk powder of NiST1 milk powder. From the milk powder, different potassium, chlorine, argon, or calcium presence that is identified by using XRF. And quantification you can do by calculating the area under the curve with a standard data you have. But here you need a standard data to identify, to quantify your materials, your system. So there are a lot of interference effect, like spectral interference effect, K line, L line of adjacent element that will overlap. Sometimes that create problem, or environmental interference like the element like sodium to chlorine. This is a light element emit weak fluorescence. So that can be easily attenuated by air or argon environment. So that little bit difficult for that. Or sometimes matrix interference like absorption enhancement effect. You will see the element can absorb or scatter the fluorescence of the element of interest, like particular element you want to find out, so that may be get absorbed, so the fluorescence, scattered fluorescence will be changes, or it can be increased. So this type of three, the spectral interference, environmental interference, or matrix interference, that can be taken care properly, then you will get the elemental analysis and very good analysis result. You can identify each element by using these methods. So far I have discussed, all X-ray based techniques like, X-ray diffraction, single crystal XRD, powder XRD, as well as, thin film XRD, then X-ray absorption spectroscopy, where I discuss EXAFS and XNES, and then I discussed a little bit about X-ray fluorescence, which is used for elemental analysis. So like X-rays, we can also use neutron for diffraction analysis. So neutron being a magnetic moment, it has a magnetic characteristic. So you'll be able to see, diffraction as well as, due to magnetic neutron scattering diffraction, you'll be able to see here. So if you see this, that I have already discussed this little bit basics about neutron scattering. So neutron, the mainly nuclear neutron scattering, two scattering is possible. One is nuclear neutron scattering. As I told, being nucleus is very, very small in comparison to the whole electron cell. The neutron electron nucleus interaction is very weak. And this nuclear, there is two type of scattering here. One is nuclear in neutron scattering, another is magnetic neutron scattering. If you go to nuclear neutron scattering, it's no form factor dependent. As I told, in case of electron scattering, that X-ray scattering, so there is a form factor varies with your sin theta by lambda. But here there is a form factor, no dependency there. and it's elastic. From the elastic scattering, your diffraction, that crystal structure, you'll be able to see. And from inelastic, that excitation, that you can mainly the phonon vibration, you can able to see here. So you can able to that both crystal structure and phonon vibration, both information you get from nuclear scattering, but from the magnetic scattering. So that magnetic scattering form factor dependency, the magnetic that is falls faster than the X-ray form factor. So, but the neutron nuclear is not form factor dependent, but magnetic one is form factor dependent. And again, from elastic, the diffraction structure, that spin structure, you are able to find out. From inelastic, the excitation, that magnons, so you can able to find out that phonon things you can able to find out. And temperature dependence, there is magnetic scattering has a temperature dependence, you will see. So neutrons with thermal energy 10 to 100 millivolt, that will mainly use the wavelength of range of 2.86 to 0.09 angstrom, that is comparable to the atomic separation of the condensed matter, so interatomic distance in this range. So that's why this Newton diffraction can be used for crystal structure analysis. The thermal neutrons are therefore useful in studying, atomic positional correlation in condensed matter physics. So you can use these thermal neutrons with the low energy. You can use here. You can see the structure factor is coming from that F square. Scattering factor is summation of nuclear scattering as well as magnetic scattering both, as it has a magnetic moment of 1.19 until mu n. That but it is zero charge. Because of this magnetic interaction, you will get both magnetic form factor and neutron, and you combinedly you will get a combination. So you see the Newton diffraction, you have a basic source is nuclear reactor here, and then the nuclear reactor monochromatic beam is coming and falling on this crystal in that sample, then the diffractant beam. It's like similar to that of X-ray diffraction. You'll be able to see wherever the Bragg's law satisfied, you can able to see that in that particular diffraction beam pattern. It's similar to XRD, but the difference type of radiation gives complementary information. Like being a neutron, there is XRD, it's an electron. So the being that complementary, that is different type of radiation source, it gives you complementary information that you can't get in case of XRD, you'll be able to get in neutron. For example, neighboring and isotope information is discriminated, that can be identified here, whereas neighbors and isotope can't be separated, discriminated using X-ray diffraction pattern. So light element can be detected like hydrogen, deuterium, those type of information elements can be detected here, but that is hard to detect in case of X-ray. So magnetic structure can be investigated using Newton diffraction, whereas in X-ray it's not possible. There is lower absorption in case of X-ray, but it needed longer time required to scan as comparison to X-ray, and its availability is very, very few, means you need a nuclear reactor to see this Newton diffraction pattern. If you see scattering from nuclei, if there is a Bragg's law satisfied, the scattering will occur from the nucleus. Newton will scatter from the nucleus. But in case of magnetic one, that there is a nuclear scattering. In addition, that you have there is possibility of magnetic scattering. If there is a Q wave vector is parallel to the magnetic spin, you can see that this is the magnetic spin, then parallel beam will not give you magnetic scattering. When you have perpendicular one, if your magnetic spin are aligned this direction and X-ray beam is coming here, then if you are perpendicular, then only you will get Newton scattering. So Newton scattering from component of magnetization perpendicular to the wave vector Q, that is nothing but 4 pi by lambda sine theta on this, depending on this equation which is perpendicular to the magnetic field, then only you will be able to get that Q perpendicular to the magnetic field, you will be able to get the magnetic information. Where in case of the Newton's nuclei scattering, with nuclei you will get crystal structure refinement, you will get structural distortion, charge error, but spin arrangement, and magnetic information you will get from the magnetic scattering. And if you see the Newton scattering structure factor, as I told from the XRD, that Fa scale is summation of Fa and that the element electron scattering into e to the power 2 pi I this coordination. So here in the Newton diffraction, that this F is replaced by that form factor F is replaced by the scattering length B. In case of neutron, how the electron beam is scattered, that I told that the band, that equation Bn is the scattering wavelength, scattering length of the nucleus. You can see here, if you see the neutron, then in the X-ray, the X-ray form factor, as I told, is proportional to the sine theta by lambda. But in case of nuclear neutron, it is form factor independent, where magnetic is dependent, is much decreasing much faster. If you see here, this is the X-rays here, that form factor for hydrogen, lithium, carbon to cesium. You can see the cesium, the form factor, if it is quite large. But in case of that, with their Z value increasing here, here from hydrogen to cesium, your X-rays, the form factor will vary. But in case of this neutron, you can see there is randomly Z value, independent of Z value. You can see hydrogen is quite big, and then lithium, and like this, it varies randomly in case of neutron. So structure factor independent. That's why neutron, the X-ray diffraction peak, you can see in case of XRD, the higher angle peak is less intense. But in neutron, you will see random intense peak, since there is no independence of scattering factor. So that's why you see higher intense peak are also large. So advantage of Newton diffraction, there are many advantages. One basic example I have given here, that as I told, that NaCl and KCl, in case of NaCl, you have higher diffraction peak, that you can able to see 111 peak in X-ray diffraction analysis. But in KCl, that because of potassium and chlorine are isoelectronic, you are not able to see this 111 peak, so they will cancel each other. So you're not able to see in case of X-ray diffraction pattern. But we will go to Newton diffraction pattern. This, as I told, the scattering length of both potassium and chlorine is different. If you see Fk minus FCl, for the X-ray, it is, if you divide it, Fk minus FCl by Fk plus FCl is 0.06, very, very low, where these are almost equivalent. That's the isoelectronic, because of electron dependence. But in neutron, you can see the scattering length of potassium is 3.67 FM, while that of chlorine is 9.5. So that this difference ratio is 0.48. Being large difference here, you can able to see that 1 peak, which is absent in case of KCl in XRD. So here in Newton diffraction, you can able to see that particular peaks. Similarly, you can see this is another, that Ni3Mn structure. You can see here in X-ray, this difference is very, very low. You will not able to see that superlattice reflection case. But in case of neutron, you will able to see that this additional that peaks that can be, you can easily see in case of Newton diffraction. So another advantage, you can see the isotope effect, as I told, that Ni3Fe, you can see here, if there is a natural neutron, Ni is 10.3, and that of nickel, scattering length of nickel is this, and that of substituted 60, if Ni 60 isotope 1 is 2.8. So there is a difference between this and this. So because of this difference, you can able to see that isotope effect you will able to see in case of Newton diffraction, or in X-ray diffraction is not possible. So isotopic separation can be possible in case of Newton diffraction. As I told, if a magnetic Newton diffraction, like you can able to, there is a Q vector is perpendicular to the magnetic field. Here you can able to see that information. As I told, in case of ferromagnetic material, what will happen if it is see this it's perpendicular and parallel spin, you will able to see only magnetic moment perpendicular to Q vector, that scattering contribute to magnetic scattering. Here this is perpendicular here, and this is antiferromagnetic. Here you can see this is in one direction. This is all our spin are aligned in one direction. This is in one direction. This other direction. They are antiferromagnetically coupled. Is ferromagnetically coupled. So because of this antiferromagnetic and ferromagnetic couple, you can able to see that magnetic information. In one example here I have shown, if a ferromagnetic interaction is there, all spin are aligned in one direction. You can see there is an additional increase in peak intensity, so that you will able to see in case of ferromagnetic interaction. But in antiferromagnetic interaction, you can some peaks can be it be absent, or some additional peak those are antiferromagnetic coupled. So those peaks you can able to see whenever ferromagnetic interaction so you will get. So so cells same as chemical cells are same, so you'll get here ferromagnetic interaction, anti-ferromagnetic interaction. Cell could be large and different symmetry because they have because being there oppositely interact, so you can get a different symmetry here. So we can see, I have given one example. You can see there is a MNO structure here, antiferromagnetic superstructure MNO FeO or nickel oxide, showing pseudo cubic unit of oxygen position. I have not shown here. See, this is the manganese atom here. You can see there. This is one up and one down, one up, one down, one up, one down. These are oppositely, like spin is aligned in this opposite direction instead of parallel spin. Here spin or opposite direction. You can see here when you go for X-ray diffraction pattern, you are able to see 1 peak and 220 peaks. You are able to 6 and 220 in few peaks you are seeing. But when Newton scattering at 293 room temperature, you are almost getting similar structure, where these two are less intense. But when you go for this low temperature at 80K in case of neutron, you can see there is 111 star, 311 peak, 331 peak. These additional peaks you are able to see. This is because of antiferromagnetic interaction. You are see those additional peaks, so you can easily get this whether it's magnetically interact or not. So those information you can able to get using a Newton diffraction studies. But Newton diffraction studies a lot of temerities, like neutron flux are very low, and it experiments takes long time. You have to get equivalent result to that of XRD. You may have to do for a whole day or more analysis, and large sample needed. In case of Newton diffraction, in case of Pauli diffraction, you need a 2 to 3 gram, even less than that. Also in mg level you can also do. In single crystal you need 0.51 centimeter, and but in case of Newton diffraction, you need very large crystals. But for Newton absorption element, there are some elements which absorb the neutron, like cadmium, Gd, samarium, or boron. Those analysis of material composing those type of element is little difficult because the neutron will get absorbed. So instead of diffraction, so you will not get any structural analysis in that case. So but we'll have to go for major facility like reactor or Palaisan source to get a nuclear neutron to do these experiments. So, but in case of XRD, these things are not at all necessary. So far in today's lecture, so I covered mainly X-ray diffraction analysis, like that. I discussed with single crystal X-ray diffraction analysis. In single crystal XRD, the information that we get mostly a 3D electron density mapping, and that from the 3D electron mapping we'll able to get atomic arrangement, how the atomics are arranged, and then you can predict the crystal structure and the bond length. Those information you can able to get in single crystal XRD, like first that crystal structure depending upon the based on single crystal XRD, how that that DNA structure was identified, that I have discussed. So the single crystal XRD mainly is studied for atomic arrangement information you are able to get. But then for grazing angle XRD, so that if you have a thin film sample, that thin film information you can able to get from the grazing angle XRD by doing depth profiling. You can able to see if the structure A, B, L is there, and A and B are the interface. They are overlapping to each other, like diffusing to each layer, and able to identify the intermetallic structure by depth profiling, or in a solar cell in the information, like particular by varying the angle of incident from 1 to 10 degree, very low angle like 1.5. So at the low angle that it will interact, that the X-ray interaction is much larger with the coating layer instead of going into the substrate. So you'll get more information about the thin film. Similarly, by using synchrotron XRD, the synchrotron XRD, I told the synchrotron X-ray source has very high brightness, they're highly collimated and highly energetic. And because of that, when you can remove that K alpha 2, alpha 1, K alpha 2 can be completely removed, you will get peaks correspond only K alpha 1. And then the most important thing is here, even at a sample concentration of very less, you can able to identify the diffraction, you can get the diffraction pattern at crystal structure with smaller time fraction. And you can do both high temperature, high pressure studies using synchrotron XRD also. Then I discuss little bit on X-ray absorption spectroscopy, that is the X-ray absorption fine structure, that is that mainly two parts, that how the exabs and exness, the two information. So these two information that gives information about that exness will give information about nearest neighbor atom, and whereas that of exabs will give you coordination numbers, that symmetry or structure, or even the oxidation state, valency band structure, those information can be found out from XNES. So that I have discussed. And X-ray fluorescence spectroscopy, that you can use that how the some of the when it you irradiate with the material, the X-ray, so it's all fluorescence will come out from the elements. So that fluorescence can be detected either by WDX or wavelength dispersive manner or energy dispersive manner. You can identify particular element. That composition analysis can be possible by using X-ray diffraction, X-ray fluorescence spectroscopy, and you can quantify depending upon the area under the curve and comparing with the standard samples. You can able to identify, can quantify each elements. And finally, that I discussed the Newton diffraction pattern. The Newton diffraction is a complementary to that of X-ray diffraction, being that Newton source are used, you get information, complement information here, like carbon, hydrogen, those type of elements are sensitive here, unable to find out that both atomic and magnetic structure of the crystalline materials here. And then in case of Newton diffraction, that like antiferromagnetic, ferromagnetic coupling, those type of in the magnetic interaction, you can able to find out. But the only difficulty is that to getting a neutron source, you need a reactor or palation facility to get that. So, so far we have discussed the diffraction techniques, and then the next class we'll discuss the scattering technique, that mainly small angle Newton scattering and small angle X-ray scattering. How that here in the X-ray diffraction or Newton diffraction, your theta is quite large here, but here in new small angle X-ray, your theta is a small low angle. That how you can get the information of that the particles information, that ordering information, those type of information we'll study in the next class. So I have gone through, being the time limit, so I have studied today many techniques. So you just go through the books I suggested. So those with the books can easily get this that air waste or BD quality, those type of characterization book you can study. You can find, you can get a broad idea about these techniques. If there is any question, you can raise. Okay, if there is no question, then we'll complete today's class here. And if you have any doubts, then you can also email me at my email ID later on also. Thank you.